radial. Bien. Perfect. Okay. I think we are live. Let me start. Welcome, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host today. Today, we're presenting Proving Strong Gravity with Black Hole Ringdowns by Max Isi. Max obtained his PhD in physics from the California Institute of Technology, Caltech, in 2018. Before moving and becoming a research fellow at the Center for Computational Astrophysics at the Flatiron Institute, he was an Einstein Fellow. It's a very prestigious fellowship that he took to MIT. Max is also a member of the LIGO Scientific Collaboration, and he works on many things, mainly on the analysis of gravitational wave signals with an special interest, I'll say, in using those signals to prove general relativity in many ways. So remember that you can ask questions over email through our YouTube channel or Twitter, and then the questions will be read at the end of the talk. So Max, take it away. Thanks for joining us.
All right, thank you, Alejandro. Let me share my screen. I hope this works, otherwise.
Yep.
All right, good.
Awesome.
So I'm very happy to be here. Thank you for the invitation. As you mentioned, I have been a member of the LIGO Scientific Collaboration for many years. And as you know, over the past several years, gravitational waves have galvanized several areas of research in astrophysics and fundamental physics. And when it comes to fundamental physics, one of the most exciting recent developments, at least from my point of view, has been the study of the ringing modes of black holes with the intention of using those kinds of signals to learn about the nature of gravity. So that's what I will be telling you about today. This is the menu I put together. I will start by telling you a little bit more about what these ringdowns are and why they are interesting. I will assume familiarity with gravitational waves to the extent that you know that gravitational waves are a thing. But if you think I glossed over something important, please let me know and we'll go back and talk about that. Then I'll explain how we can actually go about detecting these ringdown signals in our data and what kind of measurements have occurred recently and what they mean and what they might mean for the future. Okay, so to get started, the key to this whole program is the notion that black holes, when they're perturbed, when they're excited, let's say you throw MTW, you throw a book into a black hole, you will disturb its environment, you will disturb its metric, and it will vibrate in a very specific way. It will vibrate as a superposition of modes with characteristic frequencies and durations and damping rates that encode the nature of the geometry of the spacetime of the black hole. So it will vibrate with these damped sinusoids in a way that have frequencies that tell us about the structure of the black hole and whose amplitudes and phases tell us about the origin of the excitation. So you can write that as I do here at the bottom as a complex frequency, the real part of which tells you the oscillatory part of these modes of vibration, and a complex imaginary part that tells you about how fast these modes are decaying. Eventually, after you initially excite the black hole, they will initially vibrate, and then slowly it will quickly, those excitations will decay and you will be left with a stable stationary black hole. So the way I like to explain this as an analogy is just like a bell, which is something that most people are familiar with. So if you have a bell and you strike it, it will vibrate and emit sound with very specific pitches and the duration, and these tones will have certain duration, and the frequency of the noise of those tones and the duration are actually encoding the material structure of the bell, the size, the composition, how it's actually put together. And then the loudness of these different quasi-normal modes of vibration tell you about exactly what kind of perturbation got the vibrations started. And so this is the same way with black hole, except instead of sound, we have gravitational waves. And instead of learning about the composition of the bell from the frequency and damping rates of the tones of sound, we actually can learn about the structure of the black hole from the frequencies and damping rates of these gravitational wave quasi-normal modes. So the reason this is interesting is that in general relativity, we expect a black hole to have only at most 3 properties: mass, spin, and charge. For astrophysical black holes, charge we don't expect to be relevant. So this is really just 2 numbers, the mass and the spin. And those 2 properties should actually determine all characteristics of the black hole, including these modes of vibration that we should observe when we perturb it. If it's not true, and we actually observe a black hole vibrate with a frequency and damping rate that is not consistent with a given mass and spin as we expected in general relativity, then what we are observing is not a vanilla black hole in GR, in general relativity. And that could be either because we are looking really at an exotic object, or general relativity needs to be corrected and the actual nature of the black hole is not the simple, described by the simple Kerr metric, which is what describes a spinning black hole. And this should hold for the kinds of black holes that LIGO and Virgo see, in particular the remnant that is produced after the black hole collisions that we observe. This sort of program is called black hole spectroscopy, and the aim is to test this fact that all the properties of the black hole should be determined by the mass and the spin, which goes by the name of no-hair theorem. The only properties that a black hole has is the mass and the spin. So if this is true, we can leverage this fact if we have access to one of these ringdowns to do 2 different kinds of things. Well, assuming that what we're looking at is indeed a Kerr black hole, so the simple black hole described by a mass and a spin within general relativity, we can measure the frequencies and damping rates of the modes of vibration in the gravitational wave data, and from that infer the parameters of the black hole, so its mass and its spin. If we can extract or identify in the data more than one mode of vibration, then we can measure we can measure at least 2 frequencies or at least 2 damping rates. We can start trying to do consistency tests, because there's an infinite number of parameters, an infinite number of frequencies and damping rates that should be determined by just 2 numbers, the mass and the spin. So if you have access to a multiplicity of these modes, you can actually see if they are self-consistent, and if they are not, then this is evidence that the no-hair theorem is being violated. So this is a very useful resource. It's a very clean experiment that we can use to learn about the structure of the black hole spacetime in a very simplified setting. So just so that we're all clear what we're talking about, these modes of vibration that will make up the gravitational wave signal can be described by, well, are defined by a given complex frequency, as I mentioned, that has a real part and an imaginary part. And then each frequency and damping rate are associated with an angular pattern. So these are described in terms of L and M numbers, just like in usual quantum mechanics or whatever, what have you, where you have an expansion in terms of spherical harmonics. In the case of a spinning black hole, we have spheroidal harmonics, which are these SLM functions that you see on the right, but you can think of them, they are very close to the spherical harmonics that you know and love. And then for each angular number, L and M, there's an infinite ladder of modes indexed by N, which is the overtone number, that by definition orders these modes in terms of decreasing damping rate. So the higher the N number, it means that the mode, it lasts shorter, so it decays faster. And so a superposition of all of these modes is what you excite when you perturb the black hole, and they add up to make up the gravitational wave strain, which is this quantity H that we will measure in our detectors. Okay, so again, you can take this construction and parameterize these frequencies and damping rates in terms of a mass and a spin. The spin is this quantity chi, which is a dimensionless parameter that tells us how fast the black hole is rotating. And so if you do that, you can, from the measurement of F and tau, the frequency and the damping rate, you can backtrack what M and chi is and learn about the mass and the spin of the black hole. Or again, if you see more than 2 modes, you can try to do consistency and introduce these perturbations away from the prediction for a given M and chi, which are these delta F and delta tau parameters in these equations in the second set of equations. And we can treat those as parameters to be measured from the data. And so if we find that the data prefer these delta parameters to be 0, then that is equivalent to consistency with the no-hair theorem and our expectation that the black hole is fully described by a mass and a spin. Okay, so how do we actually do this? Well, ideally we would get access to a black hole somewhere, and we would perturb it in different ways and try to measure its ringing with one of our detectors. You can see our LIGO Livingston detector represented here. In practice, of course, that's not what we have. We cannot have a control experiment in which we actually perturb the black hole in a well-defined way, but what we do have access to is mergers of black holes, by which we observe two black holes start far away and slowly spiral until they merge and settle down into a final remnant black hole, which will initially be perturbed exactly in this way, as I described earlier, and will get rid of this extra excitation by radiating in quasi-normal modes that should have frequencies and damping rates that are just determined by its mass and its spin. So if we are able to isolate this later part of the signal that corresponds to the black hole ringdown, we can start doing all these spectroscopic tests and learn about the properties of the black hole and test the no-hair theorem. So the stages that I represented earlier with that simulation from 150914, those are the snapshots that I showed you, roughly map to the signal that we see at the detector, which will represent with this kind of waveform. So you'll see these wiggles represent the differential strain in the arms of our detectors. So a large value means a big strain, and then when you're at 0, it means the two arms have the same length. And so in the initial stage, when the two black holes are further apart, they are orbiting each other, they cause this almost sinusoidal gravitational wave that slowly increases in frequency and amplitude until the black holes merge and there's a big burst of gravitational waves. And at some point, the strain signal, this template, should be described by the gravitational wave emission of a single perturbed black hole. So there's a question about how do we actually identify where to look. I mean, clearly, if we're trying to target the vibrations of this remnant black hole, we won't be looking early on around the spiral regime. That would make no sense. So we want to somehow identify a region here later on that we can actually describe the signal as being an emission from the remnant. This is actually a very tricky question, which I will not go into in a lot of detail. Suffice it to say, for practical purposes, all that we need to do is define the ringdown operationally as the moment in time where a superposition of damped sinusoids with the frequencies and damping rates corresponding to this remnant black hole provide a good description of the strain. And so we can empirically try to find where that point is from numerical simulations, and then go look at the actual data and see if that is also if that works in a similar way. So of course, this kind of signal that I'm showing you here is very idealized. It's what we would have if we had direct access to the gravitational wave. In reality, our measurements look more like this. This is actual data for GW 150914, our first detection. And so actually teasing out these modes of vibration from the later part of the gravitational wave signal is a very tricky problem. And there are several approaches to actually trying to tackle it. Roughly speaking, you can split those into two. So there's on one side what you can call an enhanced in spiral merger ringdown analysis. So a regular analysis of LIGO Virgo data will take the full signal and analyze it as a whole. We want to somehow isolate the portion of the signal that corresponds to this remnant black hole later on, so we can extract those frequencies and damping rates. This first way of doing that grabs the model for the full signal and enhances it with additional degrees of freedom that control the emission in the later part, as you see represented in this plot. The second kind of strategy is to just say, let's just identify a point from which we will say this should be the ringdown, and let's throw everything away that preceded it, and let's just try to fit our data with damped sinusoids just from some time onward, and this is usually done in the time domain. I am one of the main people proposing this second type, but let me tell you a little more about the first type as well. So as I was mentioning, you could try to have grab as a standard model for what this whole signal should be, which these models are obtained from a mixture of analytic work with numerical simulations, so black holes merging according to GR. And so we can obtain this prediction of what for any given system we should see, including this later ringdown part. And we could add degrees of freedom that control the frequency and the damping rate of the ringdown part later on. This is nice because it means that this procedure is very amenable to being used with the standard analysis techniques that we apply in LIGO Virgo world. So you don't have to think about it too much, and you can just put it through our usual pipelines and try to get a measurement for these delta Fs and delta taus that have been included in this overall model for the signal. The drawback is that you are necessarily linking your measurement of this later ringdown part to the earlier regime, to the spiral and merger. And that means that your measurement might be susceptible to any systematics that came from the earlier part, or any issues that there might be with the attachment of the ringdown part to the merger part, or merger and spiral part, and so on. And so the systematics are harder to control, but it's something worth doing, and that's something that the LIGO Virgo collaboration, the LVC, has done. I'll return to this at the end. So the other strategy has it's like the flip side of what I just described, which is it has the nice advantage that you can identify very clearly the data you want and just throw away everything before it, so you don't have to worry about contamination, or that perhaps the general relativity model might not be good enough for the spiral either. So you don't have to worry about that at all if you are actually just focusing on some segment of data later on and throwing everything away before it. But actually it turns out that doing this from a data analysis point of view is very tricky. We are usually not in a circumstance like this, wherein the signal starts right at the edge of the segment of data that we're looking at. And that means that you have to rebuild all the analysis infrastructure that we have in LIGO Virgo in a different way. An intuitive way to see why this is actually harder than you may think is that if you want to isolate this late part of the signal, and you could try to just zero out everything before, let's say, the reference time, let's say it's the peak of the signal, let's say from then on it's just a ringdown. If you do this, then if you try to Fourier transform your data, which is what we would usually do to analyze LIGO Virgo data, then you would find that this discontinuity is bad and it will lead to aliasing. You can't have discontinuous data in that way without inducing lots of problems in your analysis. So what you usually would do is to try to window it smoothly turn on your data. And so you could do that in a way such that you include some support for data right before the point where you're saying the ringdown starts. But in that case, your ringdown analysis will be contaminated by this earlier part unavoidably. And so the other option would be to start your window, your ramp up, your smooth turn on of the data after the cutoff point. But in that case, you're throwing away some important data near the start of the ringdown, which, as we will see, is actually crucial for some of these analyses. So this is to say that it's actually turns out fitting damp sinusoids to just some portion of data ends up being a surprisingly difficult task. And so I myself and others have figured out how to actually do this properly. And long story short, once we've rebuilt the way that these analyses work, we're able to just pick a point in the signal, fit the damp sinusoids, and reconstruct what they were from the data. So in the example that I'm showing you here, we're fitting two quasi-normal modes. Q and M is quasi-normal mode, long-lived one in orange and a short-lived one in green, and they are reconstructing the total data that are shown in blue. And as I'll show you later, this is from 1509-14. All of this, I'm telling you this because this actually matters. So in the audience, if there's someone out there that actually wants to try some sort of analysis of this kind, if you don't do it correctly, you will have biases. And so that was actually the case for the initial sorts of analysis that even the LIGO Virgo collaborations did for the Ringdown of 150914 back before we knew this whole thing was so tricky. So what I'm showing you here is a simulation of a Ringdown like 150914 analyzed with two techniques, one in which you actually take into account of these nuances in red and one in which you don't in green. And you'll see that the green results, which are represented here by 90% credible contours, it doesn't matter, as you increase the amplitude of the signal, which is the signal to noise ratio label that you see here, it will converge to the wrong value of the frequency and the damping time of the mode that was simulated. Anyway, so all of these sort of abstract considerations actually really matter. It's a finicky problem to actually tease out these frequencies. And we want to make sure we have it right because we are trying to make big claims about the nature of space-time from these modes of vibration and so on. Anyway, so long story short, after everything I've told you, can we actually do this now? Well, for a very long time, until let's say 2 years ago or so, the standard answer would have been probably not. And that's because the traditional way of thinking about this was that we probably want to be quite conservative as to where we're actually looking. And so we want to look quite a bit of time after the peak of the signal to make sure that there's no contamination from potential effects that are not just the radiation of the remnant black hole. And that's after you wait for a while, we know that from numerical simulations that you should just have the single longest lived mode dominate the signal. And so if you can try to look in that regime, which is later on, let's say down here, and try to identify different angular harmonics, so different LM numbers of these quasi-normal modes. But that's also in and of itself tricky because these tend to be quite weaker than the dominant harmonic that is the quadrupolar L equals M equals 2 mode. So this is hard for these two reasons. So you're going late after the peak, so the signal has decayed. And also you're trying to find these secondary angular modes that are themselves even weaker than the dominant part of the signal. So if you want to do this, the traditional expectation was that you probably need next generation detectors. So this was the conclusion. Now, this doesn't factor in the fact that overtones of the dominant angular harmonic, so that N number that I mentioned, also play a role in the ringdown signal, in the description of the signal around the peak. Overtones actually allow you, as I will explain in a little bit, to move closer to the peak of the signal, where you have a better chance of actually detecting it and analyzing it more clearly. And it also means that you don't need to try to find these even weaker angular harmonics, which would be great to see, but they are just harder to see. And so once you factor in overtones, it turns out you can start doing some of these spectroscopic tests today. So let me go on a little aside on these overtones and what they are and what people have thought about them. So as I mentioned earlier, for each angular harmonic, L and M numbers, there's an infinite ladder of modes with increasingly faster decay rates. So they last shorter and shorter and shorter as you increase this N number, which is the overtone index. What you see represented here is the overtone, the tone frequency on the left, damping rate in the center, and quality factor, which is just pi f times tau on the right. And so you see that, and so you see this as a function of the black hole dimensionless spin. And so you see that the overtones tend to have quite similar frequencies. These are the frequencies, but very different times, damping rates. So there's a fundamental mode, which is the longest lived, which is the N equals 0 mode in blue. And then the first overtone, N equals 1, is down here in terms of damping rate. And here's the quality factor. So these are the higher overtones are decaying very fast with respect to their frequency, oscillatory frequency. But these are all legitimate solutions to the Tokolsky equation, which is what these quasi-normal modes are. It's this differential equation you solve to get these modes of vibration. And so they have the same ontological standing as any other modes with other different LMs. And so because these overtones are shorter lived, they had been silent for a long time, although there had been a lot of work going back to 2007, probably even before, anticipating that they should be relevant, depending on where you look at in the signal. So here are some references where people have been looking at numerical relativity simulations and trying to find these overtones at different points in time after the peak of the signal, shown here. And so people had found 1 overtone, 2 overtones, 3, depending exactly what they were doing. But it wasn't until really this paper by Giesler et al., of which I was part of in 2019, where in there we said really this whole signal can be described phenomenologically as a superposition of just tones of the 2-2 mode from the peak onward. And so the thesis or the argument in that paper is really that you don't need to worry about strange stuff going on close to the peak. You can describe the whole signals as a superposition of the quasi-normal modes of the remnant black hole, as long as you're also considering, or don't forget about including, the higher overtones. And so this is great. We can describe the full numerical relativity simulation, which is here in blue. This is the strange signal that we should see for a signal like 150914, and we can reconstruct it fully as a superposition of this fundamental mode and the overtones. Of course, the later part is dominated by the longest lived mode, and overtones are actually helping you near the peak because they are very short-lived. So these are the amplitudes of the overtones for a signal like the one I just showed you in a log scale. So in blue, you see the amplitude decaying for the fundamental mode, the longest lived mode. You see after 10M or so, it starts dominating. This is a crucial fact I omitted, but in numerical relativity, in relativity in general, we measure time in units of M, the mass of the black hole. You can add factors of G and C and so on to make it a time for a given mass, but this is what this M is. Anyhow, so around 10M, the fundamental mode starts dominating, and earlier on, you have all these other overtones decaying at increasingly faster rates as you increase this overtone number N. Okay, but it's not just about fitting this prediction of the strain very well. You can fit anything with enough number of damn sinusoids, perhaps. That's not true, but you can fit a lot of things. The crucial part is that having the overtones in your model also allows you to measure what the remnant mass and spin will be, even from that early moment in time around the peak of the signal. So on the left-hand side, what you see here is a measurement of the mass in the y-axis and the spin in the x-axis with a model that has 7 overtones. So this is the fundamental plus 6 other modes, plus 7 other modes. And you see this proxy for the measurement, which is shown in color. The lighter shows a preference for the true value that in this case, this is based from a numerical simulation where we know what the final black hole will be, and it actually gets you the right value of the mass and the spin. Of course, if you don't include the overtones and you just try to describe the whole signal from the peak onward, which has the longest lived mode, you measure something that is totally off, which is here on the right for comparison. So the takeaways are that these sort of studies, and many since, I talked about the first one, but other people have poked at this in a lot of ways since then, is that spin-aligned numerical relativity waveforms are well described by the remnant overtone model starting around the peak strain when we're looking at the dominant 2-2 harmonic. We can recover the amplitudes of consistently in time. That means we can carry out this measurement at different points in time in the signal and recover the right decay of the amplitudes expected from theory. and that overtones contribute, because actually if you perturb the frequencies of the overtones and try to carry out this measurement of the mass and spin, as I just showed you, you will find that that no longer works. And so you actually need to have the right frequencies and damping times, or at least the frequencies for the overtone, for the measurement of the remnants properties to work. So they are playing a role. And so these are empirical claims that we draw from the study of a number of numerical relativity simulations. And that's really all we need to then try to go and see if the data conform to that or not. So we should be, if general relativity is correct, we should be able to go look at the peak of the signal, measure these overtones and their frequencies and damping rates. And if they don't match what we expect from a Kerr black hole, then there's something wrong. And this is in the sense that the Noether theorem is likely incorrect, or GR is incorrect in a different, more subtle way. So as an example, here's a simulation of a measurement in which we can actually simulate having a fundamental mode and the first overtone for a signal like 150914 for the remnant of that event. And so you see on the right a simulated measurement of the deviation in the frequency in the x-axis and the damping time on the y-axis of the overtone for three kinds of simulated signals. One in which the true signal is just as we expect in general relativity, and that's in gray. So you see the true value indicated by the crosshairs is 0 and 0. So this is GR and a Kerr black hole. And we can perturb the frequency of the overtone by making it higher or lower, which are the orange and blue cases here. And in any of the cases, we can track that with our measurement, which is shown with these contours that include 90% of the probability. The two different traces are the loudness of the signal, just the ringdown signal, and that's 14 and 50. Anyway, we can do this with simulations and do this with numerical relativity simulations and show that we can actually reconstruct the modes that we inject. So in this example, we simulate a signal in which we have a fundamental mode and the first overtone in blue and orange respectively, and we can reconstruct it from data at a reasonable SNR. I think in this case it's 14, and we can reconstruct what they were, which is shown by the envelope around the solid line, which is the truth. The top reconstruction is done assuming GR is correct. Then we can turn on these delta F, delta tau parameters, and we can do the same thing again in the bottom on the right. And then what you will, the feature to notice here is that we can reconstruct the individual modes as well, but the uncertainty is larger just because we have this additional freedom in their frequency and damping rate. You can see that here as opposed to the top. Then on the left, what you see is a simulated measurement again for the same signal of the mass, the spin, and the variation in the frequency and the damping rate of the first overtone. And so in orange is the case in which there is no freedom away from the GR prediction. And so all that we're measuring is the mass and the spin. So you see here, we recover the true value. And then in blue, it's a case in which you also allow these additional two parameters that take you away from GR, and we can constrain those to be around 0 with some accuracy. Generally speaking, it's true, we'll find that we can constrain this delta F1 parameter better than we can the time. The time is trickier. Okay, so this was all just theory, in a sense, simulations. We expect this to work. So we expect that if we see a collision of black holes in general relativity, we should be able to identify the peak of the strain and model the data from that point onward as a superposition of the quasi-normal modes of the remnant black hole. If we identify more than one mode, so 2 or more, we are able to also introduce these GR deviation parameters and constrain them from the data at the same time as we measure the remnant mass and spin. So we did this back in 2019 for 150914. And so this is a measure, what I'm showing you here is the resulting measurement from 150914 data of the remnant mass and the spin, again, x-axis and y-axis, starting at the peak of the strain. and using a model that has a varying number of damped sinusoids. So in the first model, the blue one, n equals 0, we just included the slowest decaying mode, and that gives you a lousy measurement of the mass and the spin up here that is inconsistent with the expectation from the full signal, which we see in black here. This measurement is obtained by analyzing the full signal as LIGO and Virgo, as we do in LIGO Virgo regularly, just assuming general relativity. We can analyze the full signal. That gives us a measurement of the properties of the initial black holes. And assuming general relativity, we can predict what the remnant mass and spin should be. And that gives you this black contour that is shown here for reference. So if everything is working, we expect the measurement from the remnant, the ringdown part of the signal alone to match what we get from the full signal as well. So this is what you see here. If you just analyze it with one damped sinusoid, that doesn't work, but we don't expect it to work. We expect that from the peak onwards, we should need the fundamental and at least a couple of overtones depending on how loud the signal is. And so that's what the yellow measurement is. In the yellow case, we have added the first overtone to the mix. And once we do that, we are able to measure a mass and a spin that is consistent with what we expect from the full signal. If we add a second overtone, then that's also true, but in reality, the signal is not loud enough that this makes a difference. And so you're actually adding just additional freedom to your measurement, and you get this purple measurement that is just broader than what you had with just n equals 1. So this is telling us that likely we're only just seeing two modes, the fundamental and the first overtone of this signal. And that is also supported by the measurement of the amplitudes of these modes. And so if you measure what the amplitudes of the first overtone on the fundamental mode are, you will get a measurement as shown in yellow here. And so this is A0 is the amplitude of the fundamental mode, and A1 is the amplitude of the first overtone. And you get something that is clearly saying this A1 mode cannot be 0. So it has to be 0.2, so 2 times 10 to the negative 21 at least, let's say, a 90% credibility. If you add this a second overtone, so a third mode, then you get the measurement in purple, and your attention should focus on this panel, which is A1 and A2, which are the amplitudes of the two overtones. And you'll see that once you have the second overtone in there, you can zero out either one of them and it will work. You just can't zero out both of them at once. So this tells us that we're actually seeing at least clearly two modes, the fundamental and the first overtone. Okay, once we've established that, we can reconstruct what these modes were and what the signal looks like. And that's what you see on the left. So in this case, assuming a curved black hole, we can reconstruct what the fundamental in orange looks like and what the overtone looked like in green. So you see it decays much faster, but we see at least one cycle. And then we can, again, turn on these delta F and delta tau parameters to do a spectroscopic test of the Kerr hypothesis, and we get a measurement as shown on the right in yellow. And so again, this is delta F and delta tau. And as we expect from the simulations, we get something quite lousy for delta tau, but for the frequency of the overtone, there is a decent constraint because it can't be more different than 20% from the Kerr prediction at 1 sigma. And this is consistent with what we would expect with simulation. So we can actually pin down this overtone frequency to be consistent with Kerr. After we did this, then more recently, we ran away with it, and you can take some of the techniques that we use to analyze the ringdown portion alone and turn your attention to the spiral and apply that to the pre-ringdown portion of the signal. And this allows you to independently get estimates for the in-spiral, so the progenitor parameters, so the masses and the spins of the initial black holes from the spiral data alone, and the mass and the spin of the remnant black hole just from the Ringdown data alone, and that's the blue and the orange on the left-hand side. And once you have those independent measurements, you can do this sort of consistency test, which you can phrase in terms of the area law, which says that the area of the final black hole can be no less than the sum of the areas of the two initial black holes. The area of a black hole is just a function of the mass and the spin, so we can turn those mass and spin measurements into area measurements and try to see what the fractional change was from before the merger to after the merger, and that's what's shown on the right. And so we find, around 97% credibility that the area theorem was upheld if we use a model with the overtone, and a little less if we use just a fundamental a little later to be more conservative, and that's what the orange as opposed to the green curves are. This is kind of exciting because it shows we can apply these techniques to slightly different flavors of this problem. You can actually truncate the spiral at different times, earlier and earlier, and see how consistent the measurement remains with the area law. And this is what's shown here on the right. As you cut earlier and earlier in time from right to left, then you get different measurements, or like the ones I'm showing here, represented by these vertical bars. They're all consistent with the area law, except the earlier you cut, the less signal you have, and so the uncertainties tend to grow. But anyhow, this was a neat extension of this sort of ringdown analysis to also incorporate some measurement from the spiral. Of course, that was all with 15 and 914. Since then, we have detected a large number of black holes, around almost 50 black hole collisions, and these all can be, well, we can attempt to do similar measurements with a number of these. And so this was, all of these detections are compiled in the second LIGO Virgo transient catalog, which you can find as linked here. And in particular, there's a paper by the whole LIGO Virgo collaboration on testing GR with these signals, linked, as I'm showing here, which has a number of dedicated studies on the ringdown. And that includes these two plots that I'm showing you here. So for a number of the binary black holes, we were able to identify, to carry out this sort of spectroscopic test with the fundamental mode and the first overtone. So I didn't actually myself do this. The different LVC group did this. So they independently confirmed that they were able to do this with 15 and 914 and a number of other events. And those measurements are shown here on the left for 3 events that are the nicer ones on the left. And then you can combine them in a smart way and get a combined constraint on the fractional deviation of the overtone frequency with respect to the curve prediction of 0.04 plus minus 0.3, as you see here in the top left. And the LEC also carried out this sort of enhanced IMR kind of measurements, which I started with, which is instead of just looking at the ringdown alone, analyzing the full signal, adding parameters that control the ringdown portion, and trying to measure what these mode frequencies are. And so in this case, what we are doing is actually constraining delta F 2 to 0 and delta tau 2 to 0 as opposed to 2 to 1 that you see here on the left. And that's because the mode that's being varied with respect to the GR prediction is this longest lived mode, the fundamental mode. And so this sort of measurement on the right is slightly different than the one on the left. It's also telling you about consistency between the merger and the ringdown, not just between 2 different modes in the ringdown. Anyway, so these are different flavors of what we have been able to do with the recent detections. They have also been external people looking at the LIGO Virgo data who have found signals of the 330 mode in one of our detections, 190521. That's not my work, but it's also very exciting. And they're using techniques closely related to what we have developed. So anyhow, this was a brief, fast tour of this fastly developing subfield, which is trying to do black hole spectroscopy with gravitational waves and LIGO Virgo in particular. In conclusion, what I would like to say is emphasize that black hole spectroscopy can give us a particularly clean way to learn about strong gravity. there are many ways with LIGO and Virgo that we can probe the nature of general relativity of black holes, the objects that we look at. But the case for black hole ringdowns is that it's a very controlled experiment where we know exactly what should happen. We don't need expensive numerical relativity simulations. We have a very clean prediction, a very clean way. Once you figured out all these data analysis complications, a very clean way of actually checking it. Recent insights, including overtones and developments of new techniques, have revitalized this program that was sort of expected to not take off for several years from now. Although, this sort of measurements that we have been able to obtain so far, they are they're quite interesting as a first demonstration that this is possible, that they will be put to shame once we actually, our detectors continue to improve and we continue to see more systems that we can actually analyze with high precision. And the future will, with certainty, we will see many more systems that offer exciting applications of this sort of measurements. That's true for LIGO and Virgo, but also future detectors like Einstein Telescope or Cosmic Explorer, when those are built and turn on in 10 years or whenever, and also the LISA, the space-based gravitational wave observatory that will fly in 2034. Those will give us access to exquisite ringdowns with several modes, and they will really allow us to do precision spectroscopy, which will be the holy grail. But the message is that there are still many open questions and opportunities for innovation with the data that we have, but also there's a lot of room to think about what we'll be able to do in the future. So it's an exciting time, at least I think so, and I hope you agree. With that, I'm happy to take questions.
Thank you, Max, for this very interesting and complete talk. While I gather and all the other coordinators gather some questions, let me start by asking one myself, which is like for this delta, these modifications you are making. I believe there are, of course, like agnostic to any theory, right? So is there any way, or people have map those to a particular theory or something like that? Could you please comment on that? If we can get some physics from those agnostic modifications or parametric modifications?
Yeah, that's an excellent question. So, I'm an observer, so my focus is on how we actually measure those. But of course, the goal is to exactly do what you said. This sort of parametrization that we pick is fully generic and extremely agnostic, and so that's a good thing. But it's also a bad thing in the sense that when you try to actually interpret. So there's a lot of work going on to actually develop the framework to actually predict systematically what these deltas will be for different theories, and that exists for some cases. I think there are a few cases. Again, this is not my area of expertise, but I'm adjacent to that. So there are a few cases where analytically you can do it perturbatively and you can get some sort of notion of what this should be. In other cases, it will have to be numerically. The point that I would like to emphasize that is, so that's a lot of, it's a very interesting avenue from the more theoretical side. And we're seeing papers about that constantly, creating frameworks to actually do this, analogous to the PN expansion for the spiral post-Newtonian. You can actually create a dictionary mapping between these things. In general, what we expect these deltas to be not just numbers that are universal, but they will be functions of the black hole mass and the spin and any other scales that are introduced by the theory. So in general relativity, everything's mass. Everything scales with the mass because the theory is scale invariant. That will most likely not be true. As soon as you start tinkering with the theory, you will introduce some other scale. And so we have smart ways of trying to combine these measurements hierarchically so that this information doesn't wash out if these deltas are different for different sources, which is what we expect. But also in the future, we will incorporate any sort of model that theorists work on. So I would say this is an active area of research, but we will always still want to do this sort of generic thing because it's once you leave GR, anything can be. So
yes, and then just to comment a little bit on that, like exactly, because I saw one of your plots, the results are combined. could you please comment a little bit? How do you combine based on this, what we just discussed? Because it's very likely these parameters might depend on the intrinsic parameters of the source. So how, more or less, if you can tell us, how do you combine results?
I'm happy you're asking me, because I've also worked on that. So you see here that it says hierarchically combined. So the trick is in that word hierarchically, which what it's implying is that rather than assuming that this parameter takes the same value for all events and just multiplying these posterior densities, which is what these distributions are. So if you could somehow assume that this parameter is shared across all these observations, you could just like multiply these measurements and get a combined constraint that is much tighter. When you can't assume that, you have to be a bit cleverer. And the kind of techniques that my colleagues and I have developed to do that is this sort of hierarchical method, which is very widespread in the astrophysics populations or astrostatistics kind of community. It's very simple. You sort of, instead of saying this parameter takes the same value for all events, you say the true value of this parameter for each event is drawn from some distribution that I don't know, right? And so I observe these data, and they should be consistent with some true value of this delta F for each of the events. What I can do is model that distribution. Let's say I can model it with a Gaussian. And so we have a mean and a standard deviation of these delta Fs. And from the collective analysis of all these events at the same time, I can measure what that mean and standard deviation is. And if GR is correct, if the null hypothesis is correct, this should be consistent with a delta function at 0, because all events should have just delta F2 to 1 equals 0. And so that means 0 standard deviation and mean that's 0 as well. And so then we turn the problem into the problem of measuring these hyperparameters, which are called this mu and sigma of that population. Consistency with 0 means GR is correct. Inconsistency means that either there's some scatter or that they all have some mean that is not 0 or some combination thereof. From that space of hyperparameters, we can come back and predict distribution in terms of the value of the parameter itself, which is what this dotted distribution is and where this number comes from. So that's the short version. And it has broad applications, not just for this. We can do it for all sorts of things.
And I don't want to consume all the time. I have lots of questions. It's very interesting, but just to that, and how much does it depend on your probability distribution that you assume, like from your prior? If it's a Gaussian or if it's a uniform, your results, do they drastically change?
Yeah, great question. So the answer is no, because of the choice that we are making of modeling this unknown distribution as a Gaussian. That is equivalent, because the Gaussian has these special properties, it's a maximum entropy distribution, whatever, it's equivalent to measuring the mean and the standard deviation of the distribution, whatever shape it has. So it's sort of like, you can think of distributions, you can apply to them a sort of series expansion. It's an expansion in terms of moments.
And it will look like
order has a mean, to second order it has a standard deviation, and we have a kurtosis and it has higher moments. So by fitting a Gaussian, what we're doing is like measuring the mean and the standard deviation.
I see.
And so it will, at some point when we have, I don't know, 1 million detections and a lot of data, you might want to keep adding more moments to this expansion and make something more flexible. But for now, this is more than enough.
Great, thank you. So let me read one of the questions I received. This is from ricardocanna, and it's saying, could you please define the area for the black holes when they're spiraling, I guess.
Yeah, so it just refers to the area of the individual black holes in a regime when they are far enough away that it makes sense to say such a thing. Right. As soon as they are very close, there's no notion of the area of individual black holes.
Okay, and if there's a follow-up, it will appear here on my screen later. Is there any questions from the coordinators? Well, I'll click on the other questions.
Yes, I have a question for
Yes,
Maximiliano. First of all, Maximiliano, very nice the talk. I learned a lot with your talk, with the explanations. So my question is this method or technique applicable for other type of gravitational wave source? For instance, neutron star merger, since their masses are so small, or maybe could be more noisier the spiraling. Or for instance, use similar method for, I don't know, stochastic wave, gravitational waves, or something that is not with the same nature than the spiraling and kind of the
Yeah.
overtone method.
So if by the method you mean the time domain, the sort of data analysis tricks, that yes, probably that has a lot of applications to many different problems. Whenever you want to isolate some portion of the data and sort of window that and focus on that. Now, more generally, this whole, more specifically, yes, this whole program is based on the idea that you have a Kerr black hole for which, so not just the data analysis techniques, but these fitting these quasi-normal modes with these frequencies and so on. That whole paradigm is based on having a black hole that has simply a mass and a spin, and we can solve in general relativity relatively easily with perturbation theory for what this should be for any given L and M and N as a function of the mass and the spin, and so it's a very clean setup. If you had neutron stars or something else, the dynamics are way more complicated because you have matter, you have magnetic fields, you have whatever, and so if what you're forming at the end is not a black hole, but it's a hypermassive neutron star, it will likely have modes of vibration, but it will have all sorts of other stuff. And when you're in that sort of regime, you probably likely need numerical simulations to actually simulate what the spectrum will be. And so precisely one of the key goals of this project is to say, is it really what we're seeing as simple as the Kerr black hole is, or are we actually forming some other exotic object that has other properties or not? And so far, it seems, to the degree that we can say anything about this, it all agrees with just being Kerr black holes. Maybe one day we'll find otherwise.
Thank you.
Yeah, and Ricardo sent another follow-up question, which is for this spiral, I guess, for the previous question, is like, as if it scales from the masses, doesn't it trivially satisfies the area law also in the spiral?
So, during the spiral, yeah, yes. And the area law should be satisfied between any 2 points. Yeah, I guess the answer is yes.
No, but I think what he's asking is like, if you were doing the analysis in the spiral and then in the ring down, and then if it scales with the mass, which I think is what he's asking, it's the same from the spiral because the masses of this will be combined. Give it or take, maybe.
No, it's not trivial.
Okay,
because everything scales with the mass just means that you can turn an overall mass scale, but it's not actually telling you about the relative masses before and after the merger. That depends on how much power is emitted in units of the initial mass or whatever. And it will be a complicated function of the original black hole, three-dimensional spins, how they're aligned, how they were, what phases they were in, and general relativity telling you what that complicated dynamics is. And then at the other end, you get just a final black hole. And so that process is scale invariant, so you can factor out the mass and move it up or down in mass scale, but the comparison between pre and post merger, that's not trivial.
Okay. Walter, okay, yeah, please, Walter, and then if there's a follow-up, right. I'll get it.
I have a question that is not so much about the analysis, but thank you very much for your talk, Maximiliano. This is more of a conceptual question, and so in more theoretical physics, like for example in holography or those things, we talk a lot about black holes in the context of the membrane paradigm, or how the horizon of the black hole is sometimes, can be studied using hydrodynamics or using this membrane approximation, and then there are all these other problems with the information paradox that come up once you start introducing quantum mechanics. To what extent this type of analysis that you guys have been doing can be used also as a probe for some of those properties? In my area, more in holography, we define these quasi-normal modes as the poles of the green functions, right? And with some boundary conditions that we have on the horizon, right? And if you change the horizon, what we call the horizon, the event horizon for something else or a firewall or something like that, then the quasi-normal modes are no longer the quasi-normal modes, but something else. To what extent is this can we use this as a probe for those properties?
Well, I think you answered your own question because as soon as that's exactly the hope. That's exactly the idea behind this program, right? Like if you have any sort of effect playing at the horizon scale that changes the boundary condition for these quasi-normal modes, the frequencies and damping rates could be completely different, or the dynamics could be different. You could get echoes, you could get other phenomenology after the signal. And the hope is that this sort of analysis is sensitive to that, right? Like as soon as you depart from the specific Kerr functional form for these frequencies and damping rates, we should be able to pick that up. Now, I'm not an expert in how easy it is to construct stable models that are vastly different from Kerr or not, but this is exactly the idea, right? If you're modifying the boundary conditions at the horizon, you will alter all these features and the ringdown, including the ringdown. Any sort of modification at horizon scale or around the light ring, that all is being probed by this sort of measurement. We still, again, as far as I know, I don't have a direct dictionary to translate these delta Fs to any specific model. And I'm sure that's been worked out in some cases. But yeah, that's exactly the idea, is that we want to know if there's something weird going on, like what you described.
Okay, thank you. And I think, yeah, we are past the hour. So let us again, thanks Max for this wonderful webinar, and let's keep in touch for the next one. Thank you. Bye, everyone.
My pleasure. Goodbye.
Boom, we are not